Let's start with what is magnetoresistance. Magnetoresistance is the tendency of a material to change the value of its electrical resistance when we apply external magnetic field. There are various phenomena which can be called magnetoresistance, but here we will discuss only TMR, tunnel magnetoresistance. As the name suggests, tunnel magnetoresistance uses a quantum phenomena called tunneling effect. We use a very thin insulating layer, a few nanometers, sandwiched between two ferromagnetic layers. As you might know, in memory device we need to have two physical states to define them as 0 or 1. So we can use this structure as a memory bit by assigning the low resistance state as 0 and high resistance state as 1. This sandwich structure is called as magnetic tunnel junction. But now you would be wondering what is really happening here, so we should dig a bit into the physics of this phenomena. If we look into the difference between normal metal and a ferromagnetic metal, one thing you might know is that in ferromagnetic metals we have unpaired electrons. That means number of electron with up spin and down spin are not equal. That's not the case in normal metal. Now these unpaired electrons give rise to net spin polarization. This is also the reason why we have net magnetization in the ferromagnetic metals. The spin polarization is calculated from the spin-dependent density of states at the Fermi energy. To understand why resistance of the parallel and anti-parallel orientation of the two magnetic layers is different, let us take a look on the amount of current passing through this structure in these two cases. Major point to note here is that an electron with up spin can only occupy a state with up spin and vice versa for down spin. Assuming this, if we see the current, that is number of electrons passing through the MTJ in parallel and anti-parallel configuration in terms of the product of density of states of two magnetic layers, we can see that in the anti-parallel case the current is smaller. That means the resistance is higher, vice versa in parallel case. This was a simple explanation of TMR effect so that we are able to talk about STT-MRAM. Before that, it is also important to note that in the our MTJ structure, both ferromagnetic layer are not identical. One of the ferromagnetic layer is called fixed layer. That means its magnetization is pinned and it can't be changed by small magnetic field. And another one is called free layer, which could be easily switched by a small applied magnetic field. So we can see that we need to apply an external field for switching of MTJ. But there are other ways as well to do such switching. Let us introduce spin transfer torque. An electric current is generally unpolarized, consisting of 50% spin up and 50% spin down electrons. A spin-polarized current is one with more electrons of either spin. By passing a current through a thick magnetic layer, fixed layer, one can produce a spin-polarized current. In other words, we can use a ferromagnetic layer's spin filter. And if a magnetic layer acts as spin filter, then it must also experience a torque. Really? Why? Because the principle of angular momentum conservation. This effect is called spin transfer torque. Using spin transfer torque effect and spin filter, we can now understand how switching of STT-MTJ happens. When we have to switch from anti-parallel to the parallel configuration, the current is passed from free layer to the pinned or fixed layer. That means electrons flow from pinned to free layer. The current is polarized in the pinned layer magnetization direction. Current provides spin transfer torque to let the magnetization change to parallel state. In the other case, when we have to switch from parallel to anti-parallel configuration, the current is passed from pinned to free layer. The current is polarized in the free layer magnetization direction. But the minority anti-parallel spin electrons are reflected on the interface between pinned layer and barrier. The anti-parallel, reflected electrons return the fixed layer and provide spin transfer torque to let the magnetization change to an anti-parallel state. As current flows through the layer of opposite polarization, electrons will change their spin, then the number of spin up and spin down will no longer be the same. As mentioned above, when we try to change the state of two ferromagnetic layer from anti-parallel to parallel, we let electrons flow from pinned layer to free layer. Let the spin-up electrons provide spin transfer torque and make the polarization of free layer to change. For parallel to anti-parallel, electrons flow from free layer to pinned layer. Spin-up electrons is gonna pass through the pinned layer due to the same polarization, while the spin-down electrons would be reflected back to the free layer and provide spin transfer torque. Let the polarization change to down.